Welcome to Physics Live once again. In the previous lecture, we were discussing the integral transformation and the different properties and the usefulness of the integral transformation. Then we have discussed the Fourier transformation, and we had already introduced the another transformation called the Laplace transformation, and the definition of Laplace transformation was given. But today we will discuss the Laplace transformation in great detail. Okay, and the usefulness of the Laplace transformation will also be discussed in this lecture. So put the heading of Laplace transformation. This is another class of integral transformation. Laplace transformation. So in case of Laplace transformation, the kernel takes the form which is something different from the Fourier transformation. And the definition was given as Laplace transformation of some function of t, I say, is given by 0 to infinity ft e to the power minus st and dt. So you can easily say that here the kernel is e to the power minus st, which will help you to convert the one function to another. Okay, another function of another variable. The function of t variable will gets converted to function of s variable. Okay, so let's start the discussion in great detail. So applying this definition, we can find out many Laplace transformation of many functions. Suppose you are asked to find out the Laplace transformation of a constant 1. Okay, so any constant, it may be some 2, it may be some integer, it may be some constant. Okay, all these things can you be obtained with this help of the first formula. So if we are asked to do the problem Laplace transformation of constant 1, then simply put it here, e to the power minus st dt. You have to integrate it, e to the power minus st minus s 0 infinity, this is nothing but 1 by s. If you are asked to do the same thing for 2, then it will be nothing but 2 into 1 by s, because if we take the 2 as common, then 2 into Laplace transformation of 1, which results into 2 by s. Okay, so by applying these definitions, we can also find out the general expression of any power of variable. Suppose you are asked to do the problem for this case. How can you do this? Simply you have to integrate with a great accuracy. Otherwise it will be very difficult. Okay. So integration is must here. So the integration process should be very much clear to you. Now in the place of ft we have placed t to the power n as a function, e to the power minus st as the kernel, and the dt. Okay, so how can we integrate? Let us change the variable st to another variable z, so that is dt will be dz. Limit should be identical at t is equal 0, z is 0, t infinity, z infinity. So the limit becomes same, but the variable t changes to z to the power n 1 by s to the power n. Okay, e to the power minus z dt. Now you have to integrate this and after integrating simply by gamma function, you can be able to obtain, that is, this is n plus 1, we can convert it as z to the power n plus 1 minus 1. So this is nothing but gamma n plus 1, and this is divided by Sn. Okay, in the factorial form you can also write n factorial divided by s to the power n. So this is the general formula of Laplace transformation of t to the power n, that is either t n factorial by s to the power n or gamma n plus 1 by s to the power n. So When t is equal 0, sorry, n is equal 0, that is Laplace transformation of 1, it is nothing but 0 factorial by s to the power 0, 1, 1, sorry, something is wrong here. Oh, okay. So here when we change this dt to dz, dt is nothing but dz by s. So dz by s, so here is to the power n plus 1, is to the power n plus 1, so is to the power n plus 1, so here will be s, 1 by s, which resembles simply with the help of the previous one. Okay, so in this way you can verify the general formula, is it is correct or wrong. That I have already verified, and some mistake have been done here, so I have corrected the mistake here. So in this way you can easily check whether the formula is correct or wrong. Okay, now let us proceed further. Likewise, applying the definition formula, you can be able to obtain many Laplace transforms of many functions. I not at all interested to write or to prove the Laplace transforms of all these functions, because it will take a very long time and the actual purpose of this lecture will not be served. So I must go into the tabular form, and you can check by the help of this definition that these formulas are true or not. Okay, so let us uh, use a tabulated form. Okay, okay, this is nothing more difficult. So you have to remember some of the Laplace transforms of the function. The first one has already been discussed, second one has already been discussed. Okay, so let us proceed for the Laplace transform of e to the power at. How can you derive this? Put the e to the power at in the functional form and e to the power minus st, so it will result e to the power minus of s minus a. Okay, so likewise here when e to the power minus st was present, this was 1 by s. When e to the power minus s was present, it will be 1 by s minus a. Okay, simple. But here one case should be considered, s should be greater than a. Okay, the second one, like this you can also find cos hyperbolic at. How can you arrive this? It is very simple, because cos hyperbolic at can be easily converted to the exponential form e to the power at plus e to the power minus at divided by 2, and you have to apply both the Laplace transform on e to the power at and e to the power minus at, so that you will result into s by s square minus a square, provided the condition also a square greater than a square. Okay, okay. The next one, Laplace transform of sine hyperbolic at. The same thing will be present here, but in this case you will result into a by a square minus a square. Okay, a square greater than a square, the condition will remain same. Next we have to find out the Laplace transform of cos at. How can you do this? You have to change the cosine into the exponential form first. Next you have to integrate with the help of this definition. Nothing more difficult to you. Okay, so if you do this, then you will be able to obtain a square plus a square. There is nothing more difference between sine hyperbolic and sorry, yes, sine I have chosen, so in the numerator always s will be present. Okay, so you can easily notice that cos hyperbolic at contains s by square minus a square, and cos at Laplace transform of cos at contains s by square plus a square. Only the difference is the denominator sign, but the numerator remains same. Okay, the next one is The Laplace transform of sine 80, this is similar to this but a square plus a square. Okay, and here the condition, this is not the condition here, a should be greater than 0. Here the condition is this. Okay. Okay, so these are some formulas, that is the Laplace transformations of some of the functions which are very often used in our discussions. Okay, so now we will discuss some properties of the Laplace transform which also help us to do many jobs. Okay, why I am discussing these? Because at the end of this we will going to show you how can be differential equation solved with the help of Laplace transform. Okay, the next thing is properties. The first property is called linear property. Laplace transform of some function f1t with some coefficient a1 or a, and f2t it may be plus minus. It will simply result a into Laplace transform of f1t plus minus b into Laplace transform of f2t. Okay. Second one, this is called linear property. The next one is scale changing property. F of at. Suppose you are given a function of this. The Laplace transform of this becomes 1 by a. F of is by a. It is very simple to prove. By putting this function into this definition, you can be able to obtain this. 3. This is called change of scale property. Next one, first shifting theorem. Laplace transform of ft e to the power माइनस at पहले प्लस लेते हैं हम, तो एफ टी टू द पावर एटी अगर ले तो Laplace transform becomes f of s minus a. Okay, how can this be arrived? By putting this function into this and by integration you will be able to obtain this. Okay, now why I am discussing these formulas? Because suppose you are given to find out the Laplace transform of consider some, okay, e to the power 2t sine 40. You are asked to do the Laplace transform of this function. So here the exponential term is present with positive coefficient, positive exponent, and another function sine 40 is present. So the Laplace transform becomes f of s minus 2. Now the Laplace transform of sine 40 you have to evaluate. You know that sine 80 Laplace transform is nothing but a by a square plus a square. So a by a square minus, sorry, plus a square means 16. Now f of s becomes this a by a square plus a square, but here f of s minus 2 is present, so here is minus 2. So this will be the Laplace transform of this. So with the help of these formula we can easily find out the Laplace transform in one single line without solving from the definition. It is the importance of the discussing the formula. Likewise, similarly you can be able to obtain that when the exponent ft of e to the power minus at will be present, not plus, minus at will be present, you have to find out the Laplace transform of this, then it will result f of s plus a. Okay, this is known as the first shifting property. Now okay, suppose a function gt is given to you with the form f of t minus a for t greater than a and 0 for 0 less than t less than a, and you have to find out the Laplace transformation of gt. Okay, in that case the Laplace transformation of gt will be e to the power minus as fs. How can you prove this? Let us take an example. Suppose gt is 0 and 0 for 0 less than t less than 1 and sine of t minus 2 for t greater than 2. You have to find out the Laplace transform of this. So Laplace transform of gt becomes, so 0 to 1 has no limit, so 2 to infinity sine of t to e to the power minus st dt. Now let us take t minus 2 into another variable z, so that dt will be dz. The limit will get changed, tz at t is equal to z is equal 0, t is equal infinity, z is equal infinity. So it will get result 0 to infinity sine of z e to the power minus s, t means z plus 2, z plus 2, dt means dz. Okay, so e to the power minus 2s will be out, 0 to infinity sine z e to the power minus sz dz. Now this is what? This is like e to the power minus st sine t dt, which is the Laplace transform of sine z. So you can easily write it as e to the power minus 2s Laplace transform of sine t. Okay, so that the general formula becomes e to the power minus as. Here a is 2, so e to the power minus 2s Laplace transform of the function Laplace transform of sine t. The formula gets verified. Okay, so let us move on further. You can apply the formula to evaluate many form of the Laplace transforms. Now let us discuss the derivative, Laplace transform of derivative of a function. It is very much crucial because you have already seen in the Fourier transform that ultimately we have to find out some derivative, Fourier transform or Laplace transform of some derivative of a function, so that it will be supplemented in the differential equation to solve further. So for this, Laplace transform of single derivative of ft, what does it give? As fs. Okay, write it in detail. So Laplace transform of ft minus f0, it gives out simply this, that is as this I have write as fs minus f0. Okay, so it is the time to prove it. Proof. Laplace transform of f prime t, so 0 to infinity f prime t e to the power minus st dt. First function integration of the second minus derivative of first function integration of the second 0 to infinity. So by putting infinity here, exponential part becomes 0. uh, it does not depend at all the if infinity. Okay, and by putting 0, this will become 1 and this will become f0. So minus of f0 coming out from this, and this is what, 0 to infinity to the power minus st simply Laplace transform of ft. So s fs, so the formula gets verified. Okay, similarly you can also be able to find out the Laplace transform of second order derivative of t to be a square Laplace transform of 15 minus a square, sorry, this is some, okay, you can prove it by assuming this. Suppose f prime t is gt, so it gets result that Laplace transformation of g prime t. Now Laplace transform of first order derivative is this, so s Laplace transform gt minus g of 0, g of 0, g of 0. So this is also Laplace transformation of f prime t minus g0 means f prime 0. So Laplace transformation of this becomes this. So a square Laplace transformation of f t minus s f0 minus f prime 0. This is the final result. So Laplace transformation of double derivative of a function is a square Laplace transformation of the function minus s f0 minus f prime 0. Similarly, you can generalize now. You can generalize further Laplace transformation of a triple prime t, nothing but s cube Laplace transform of 50 minus a square f 0 minus s f double prime 0 minus, sorry, a square f0 minus s f prime 0 minus f double prime 0. Okay, so you can also obtain the generalized form Laplace transform of nth order derivative of t is to the power n Laplace transform of the derivative of the function minus s to the power n minus 1 Laplace transform this minus s to the power n minus 2 f n minus 2, sorry, single order, no, so single order, so f prime 0 minus s n minus 3 f double prime 0 and so on up to s n minus n. Okay, so s f of n minus 2 0 minus f n minus 1 0. This is the general formula. You can easily check by putting the values of n from this and from this and from this. You can easily check the general formula. So I want to put it in a box because it is a very valuable formula. Okay. Okay, there are something like the derivative. You can also find out the integration of a function, Laplace transformation of integration of a function. Suppose you are asked to do Laplace transformation 0 to t ft dt. This is simply fs by s. Laplace transformation of the function divided by s. You can also prove it. I want to show you the proof of this. It is quite interesting. So suppose you consider phi t to be 0 to t ft dt. There is also the t variable dependent function. So after resulting the integration by putting the value of t, it will result into another function of t. So that phi prime t becomes ft. Okay. So you were asked to find out the Laplace transformation of phi t. Okay. Now phi prime t, if you do the same thing, then you will able to obtain s Laplace transformation of phi t minus phi 0. Now phi 0, what is the value of phi 0? Phi 0 simply means 0 to 0 ft dt, which result no area is covered. Okay, so it gets result to 0. So it will result 0, and this will result what? S of Laplace transform of this 0 to t ft dt, and this is what? Laplace transform of ft. Phi prime t is ft. So you can write Laplace transform of 0 to t ft dt is simply fs by s. Okay, this is proved. Next, it is quite more interesting formula. The next one, which is Laplace transform of t to the power n ft. It is very often used. What does it give? Minus 1 to the power n dn dsn fs. That is the Laplace transform of the function. How can you prove this? Proof. So for this, at first I want to write the definition, what we have learned at the beginning of this lecture. 0 to infinity to the power minus st ft dt. Okay, now dds of fs means, what does it means? If we uh, take the derivative on both sides with respect to s, then it will give minus s ft e to the power minus st dt 0 to infinity. So it gives, what does it gives? The minus s Laplace transform of the function ft. Okay, so I have done some mistake with respect to s. I have done, so there will be some t, not s. T will be coming out, minus t will be coming out in front. Okay, so this, now we can write it as minus of mm, So this is also dependent on t, right? This is also dependent on t. So the total function now becomes tft. So we can easily write that Laplace transform of tft, not simple ft, as because we have mistakenly took the a's outside, so we have write this. But when um, you are given t in front of the ft, then the function becomes tft, not simply ft. Okay, so minus Laplace transform of this, so you can write Laplace transformation of tft is minus 1 dds of fs. So this is for the t to the power 1, right? T to the power 1, d1 ds1 fs minus 1 to the power 1. Okay, so when t square will be present, minus 1 to the power 2 d2 ds2 fs will be obtained, and so on up to n. At t to the power nft we will obtain this formula. So this is proved. Okay, this can be proved by the help of mathematical induction method. Likewise, we have another important formula, Laplace transform of ft divided by t. This gives simple s to infinity fs ds. This can be proved in a similar way. Proof. So at first you have to apply the definition, fs 0 to infinity ft e to the power minus st dt. Okay, so fs ds s to infinity result into as ft e to the power minus st and ys. Okay, so ds also present and dt was there, so 0 to infinity and s to infinity. Now this gets result, we have to um, change the limit. There t is equal 0 to infinity was present, so this limit should be taken outside and s to infinity is taken as inside, and it if t does not depend at all on s, so if t is taken outside this integral, and e to the power minus st ds is there. At first we have to evaluate this integration, then we will do the this. So t is equal 0 to infinity ft, and this gives out e to the power minus st divided by minus s. By putting s and infinity, by putting infinity, e to the power minus infinity will result 0 minus of e to the power minus um, uh, minus of e to the power minus st by t will be obtained. Okay, so minus of e to the power minus st by minus minus plus t will be result out from this integration, and this will become dt. Now the function becomes ft by t, ft by t into e to the power minus st dt, t 0 to infinity will result Laplace transform of ft divided by t. So this gets the proof of this. Okay, I think it is understood by you. Now these are enough to discuss to serve our purpose. Okay, so we will quickly shift to the inverse Laplace transform. Whatever we have discussed here in the Laplace transform, if we side change the Laplace to the other side, it will give the inverse Laplace transform. So I will draw a table to understand this thing. So the first one we have discussed, Laplace transform of 1 is 1 by s. So in a similar way you can say inverse Laplace transform of 1 by s is 1. Okay, we have discussed Laplace transform of t to the power n is n factorial by s to the power n plus 1. Better to say gamma n plus 1 s to the power n plus 1. It will result Laplace inverse of 1 by s to the power n, means n minus 1 is substituted. So n minus 1 is substituted, so gamma n 1 by gamma n t to the power n minus 1. Okay, because s to the power n plus 1 may not be given sometime, so you have to change your power accordingly. This next one we have discussed Laplace transform of e to the power at 1 by s minus a. So you can easily say inverse Laplace of 1 by s minus a is e to the power at. Likewise, for cos hyperbolic at we have write a by s square minus always s. So inverse Laplace of this will be cos hyperbolic at. Similarly, Laplace sin hyperbolic at a by a square minus a square. So inverse Laplace of this. So you can easily check that once you find out the Laplace transform of a function, inverse is nothing. Similarly will be sine and cosine. You have written that uh, from the first shifting theorem that Laplace transformation of e to the power at plus minus ft gets out f of, for plus is minus a, for minus is plus a. So inverse Laplace of f is minus plus a will result 1 by 1 by not 1 plus minus e to the power plus minus 80 and ft. Okay, 9 cos of 80 is by a square plus a square, Laplace of sin 80 a by a square plus a square. So okay, now we have learned the derivative f prime t to be equal to sfs minus f0. So inverse of sfs is nothing but f prime t plus f0 with some delta t. It should be carefully noticed. At t is equal to 0, only the value of uh, f0 will survive, otherwise the value will get cancelled. Okay, 10. The Laplace transformation of 0 to t ft dt we have learned fs by s. So inverse Laplace of fs by s, nothing but 0 to t ft dt. Again, you can prove that Laplace transform of f of t minus a u of t minus a is e to the power minus as fs. What is it? Where u is the unit step function, that is its value is 0 for t less than a and 1 for t greater than a. Okay, in that case the Laplace transform becomes this. So the inverse of this becomes e to the power minus a s fs f of t minus a u of t minus. Again you have to think that its value is 0 for t less than a, 1 for t greater than equal a. Okay, I think these are enough for our purpose. So next I will show you how to solve the differential equation with the help of this Laplace transform. Let us find the problem. Hmm, which problem? Which problem should we try? Which problem should we try? Okay, suppose pick up on this problem. Hmm, okay, suppose the problem is um, y double prime minus 4y prime plus 4y is 64 sine 2t, and the initial condition is y at 0 0 and y at y prime at 0 is minus 1. So for this we have to take the Laplace transformation on both the side, and we have to apply the differentiation formula. What was the differentiation formula? Laplace transform of first derivative of this ASFS minus f0 and Laplace transform of second order derivative was s square fs minus s f0 minus f prime 0. Okay, so taking the Laplace transformation on both the side, we get Laplace transform of y double prime minus 4 into Laplace transformation of y prime plus 4 into Laplace transformation of y is 64 into Laplace transform of sine 2t. So this will give a square y bar. What is y bar? We have taken y bar as Laplace transformation of y. A square y bar minus s y 0 minus y prime 0. This is this minus 4. Laplace transform of y prime means this. So s y bar minus y 0 bracket close plus 4 y bar is equal 64. What is the Laplace transform of sine 2t? A by a square plus a square. A square plus a square means 4. Okay, so 128 divided by a square plus 4. Now we will put the value of y0, y prime 0. So this will get cancel out, this will get cancel out. We obtain a square minus 4s plus 4 of y bar minus y prime 0 minus 1 plus minus 4s. Okay, from this we get this, and from this we get this is equal 64 128 divided by a square plus 4. So a square minus 4s plus 4 y bar becomes mm, here one y bar. Oh, I have taken this one, no? So this will not be present here. Okay, so 1 plus 128 by a square plus 4. We can keep it as it is. By solving further, the result will get complicated. Now y bar becomes, this becomes what? S minus 2 whole square. So divide this 1 by s minus 2 whole square plus 128 divided by s minus 2 whole square into a square plus 4. Okay, now you have to break this into partial fraction. It is the difficult thing to do in this part, otherwise the problem is very easy. So after doing the partial fraction, you will get 8 by s minus 2 plus 16 by s minus 2 whole square plus 8s by a square plus 4. Now you simply apply the inverse Laplace transform. So y is nothing but inverse Laplace transform of y bar. So inverse Laplace transform of inverse Laplace transform of this. First 1 by a square. Shifting theorem is applied here, so e to the power minus, so e to the power 2t, and 1 by square means 1 by s to the power n plus 1. So 1 by s means gamma n divided by t to the power, let us see the formula, 1 by s to the power n, 1 by gamma n t to the power n minus 1. So 1 by gamma 2 means 1, t to the power n minus 1 means 1. Okay, minus, this is 1 not prime, minus 8 into, okay, so 8 into 1 by s minus 2, so e to the power, shifting theorem is applied here, e to the power 2t, then 1 by s, 1 by s means 1, so nothing appears here, so plus, okay, 16 into Laplace inverse of 1 by s minus 2, this is nothing but the same thing, this plus 8 into s by s square plus s square means cos of 40, cos of 2t, not 40, so this and this get sum, so 17t e to the power 2t minus 8 e to the power 2t plus 8 cosine of 2t. This is nothing but the solution of the differential equation, which is very much easy, but to get the partial fraction it becomes sometime difficult. So by once you find out the partial fraction, it will be easier to do the further steps, and you have to remember all these formulas at all. Okay, this is very much important. So in this lecture we have discussed the basic properties of Laplace transform, as well as how to prove some properties we have also discussed here, and how to use the Laplace transform in solving the differential equation is also been discussed. Thank you very much for watching.